Hey everyone, let's work on this example called charge on spheres. In this example, we have two identical small charged spheres. They each have a positive charge Q. We don't know the magnitude of Q, however, and we know the mass of them, of each charge. They hang in equilibrium. We know the length and we know the angle. We have to find this charge. So the first thing is to think, well, why did they hang in equilibrium? And this is because all of the forces are going to balance. So once we figure that out, we know, well, let's go ahead and start by drawing a free body diagram. So just pick one of the charges and draw the free body diagram. So I'm picking the charge on the left here. We know that there's a tension, so there's a force pointing away from the object. We know that two positive charges repel each other. There's an electric force pointing away from the second charge here. And we know there's always a weight going straight down, Fg. Whenever we have a diagonal force, we like to draw the components, Tx and Ty, going up, Tx going to the right. And we are given the angle theta, which is up here. We're in equilibrium, so the next thing to do is to sum up the forces equal to 0 separately in the x and in the y directions. So we can go ahead and write that down. Sum of fx equals 0, sum of fy equals 0. And let's sum up our forces in the x. We have Tx and Fe are the two forces. We're going to do Tx minus Fe since Fe is going to the left. And then in the y direction, we'll do Ty minus Fg since Fg is going down. Go ahead and write down the components in terms of the angles. Tx is opposite the angle, so it's going to use sine. The hypotenuse is t, so t sine theta. And go ahead and bring Fe to the other side, equals Fe. And then t cosine theta for Ty, since it's adjacent to the angle, that's equal to Fg. So now what? We have written our equations. Well, let's remember what we're trying to solve for. We're trying to solve for Q, which is a variable that is found in the equation for electric force. So we know that we need electric force. However, we don't care about tension, so let's go ahead and eliminate tension. How do we do that? Well, the easiest way is to go ahead and grab this equation and bring it over here. And if you've never used this trick, it's a good trick to know. Now, to get rid of tension, we can divide the two equations. When we divide them, we know that the tension is going to cancel out, and we know that sine of theta over cosine of theta simplifies to tangent of theta. That's why this is a nice trick. It really simplifies things. This is going to equal to Fe divided by Fg. Let's go ahead and get Fe by itself, since that's what we're going to need eventually. So Fe is going to equal to Fg times tan of theta, and Fg is just a weight mg. Okay, so we have an expression for Fe. How is that going to help us find Q? Well, let's go to the side here, and let's write down what Fe is equal to. Fe, Coulomb's law tells us that is Coulomb's constant times the magnitude of the two charges, right? We're only looking at the magnitude of the charge. We've already taken care of the directions. Divided by the distance squared between them. The distance between them, we can call it r. So r squared. But we can go ahead and rewrite this as ke times q squared, and then we can write r as 2 times a. So 2a squared. Now we're ready to get Q by itself. We're going to go ahead and multiply by 2a squared. And we're going to divide by ke. And that is what Q squared is going to equal to. So the next thing is to go ahead and take the square root of each side to get Q by itself. So Q is equal to the square root of Fe. And you know what, let's go ahead and write in what we know for Fe here. Let's go ahead and put that in already. So Fe here is the mg tan theta. And then we have times 2a. Now, what is a? Well, since we have L and we have theta, we can go ahead and write a in terms of L and theta. So we know that a is opposite, so a is equal to L sine theta. So let's plug in that for a. So L sine theta, that's going to be the a. And we square all of this. And then we divide all of this by KE. And that will allow us to find Q. So all that's left is to go ahead and plug in all of these values. Q equals square root of M, which is right here, which let's just say 0.03 kilograms, times 9.8 times tangent of 5 degrees. And then we're going to multiply by 2 times 0.15 meters times sine of 5 degrees. And all of this is going to be squared here. And then we're going to divide all of this by Coulomb's constant, which is 8.99 times 10 to the 9 newtons meter squared per Coulomb squared. But all the units will simplify and leave us with coulombs when we're done. The final answer is 4.42 times 10 to the negative 8 coulombs. So that is the magnitude of the charge on each sphere that will allow all of the forces to balance each other out, and it will allow these charges to hang in equilibrium.